This time we will see some example of deflection calculation for beam. So first example here is example 9.1. It says what is the maximum deflection of the following beam. For this beam where modulus of elasticity E is 29,000 ksi and moment of inertia I is 1200 inch to the power 4, and the beam span is 18 feet. It's a cantilever, that means fixed here, free here. Now, what is the equation for this beam? So we should go to back to our table, find the equation which is good for cantilever uniformly distributed load. So go back. So cantilever beam, yes, I found my equation here as this one. See, it's a cantilever beam, uniformly distributed load, maximum deflection is here at the end. And what is the maximum deflection? And now here, if I use uppercase W, that means uppercase W is total load, small lowercase w times span. So it is uppercase W L to the power 3 over 8 EI. Or if I use smaller case W, which is uniformly distributed load, it will be smaller case lowercase w L to the power 4 over EI. So let us see what I used in my solution. Yeah, I use here lowercase, so W L to the power 4 over 8 EI. What is W? It is lowercase. Lowercase means uniformly distributed load, kip per feet or pound per feet or Newton per meter, this kind of load. So kip per feet. Now you can see here, you need to be careful about the unit. Units must be consistent. Here L is 18 feet, so it is 18 feet. Your load is kip per feet, so both are feet, okay. But see, modulus of elasticity is ksi, inch to the per square inch. Here is to the power 4. So you need to be careful about unit. So what I did here, I divided by 12 to make it kip per inch. Now why I divided? If I have 3 kip per feet per inch, I will have less. So 1 divided by 12, so less load. Then L I converted into inch times 12, then it became inch. Then 8, then my E as it is, because it is K and inch square. Then my load is kept. So if I if the load is given in pound per feet, then this should be 10 to the power 6 to make it pound psi. So you will have to be careful about the unit for calculating deflection. Now here, after calculation, we found here 1.95 inch. Now in the equation listed, there's a negative sign here. Negative sign means downward. Most of the cases in beam, the deflection is downward, so we do not like to use the negative sign. You can use it. If you use negative sign, then tell clearly that what does this means, is upward or downward. So it is a downward, and 1.95, it makes sense for this beam. So this is a very simple example to calculate the deflection. Now if your equation matches exactly available in the table, you can directly use it. Now next example will tell you about superposition principles. What is superposition? If there are several loads and no equation is available for all this load together, in that case what we do, we separate it. First we determine deflection for this, then this. So we will see it here. The question says what is the maximum deflection of the following beam. Modulus of elasticity is given, moment of inertia is given. Assume the beam is linear elastic. And something else I should tell you that they did not tell anything about the self weight of the beam. That means they are telling us to neglect the self weight. Okay, so for this beam, if we so what is this beam? Is total 8 feet. There is a UDL, that means uniformly distributed load 4 feet, that means L by 2. There's another load here. Now if you go back to this table, you will not see any beam like this exactly. But what you can find? You can find a beam which has load of this 50% UDL, and there is a load here concentrated separately. Let us go where you can find it. So be careful, slowly. Yes, you can see it's a cantilever beam, L by 2 is uniformly distributed load. For this case, the maximum deflection here at the end is 7 WL to the power 4 over 384 EI. So we can solve for this kind of load. But in our beam, there's another load here. Can we solve it? Okay, go and find it. Yes, it looks another kind of beam. Here, this distance and this distance is not same, is not equal. So for this kind of beam, the maximum deflection is P A square. A square means distance from here to there. Parenthesis 3L. L means total span is L. A means here to there, and EI. That means we can use this equation and this equation separately and then combine it. This is called superposition principle. Now this is valid if your beam is within linear elastic region. That means summing up both will not exceed the linear elastic. Now if it exceeds the linear elastic, the concept in strength of materials will not work. So here in this course, strength of materials is a very basic course. We assume all the beams, all the materials are within linear elastic. So we can use this equation. Okay, so what we will do here, so first we will determine the deflection for this at this point, then we will find deflection for this load at this point, then we will sum up. How to find for this? We saw the equation, just we saw this. There's a negative sign here, we did not use because we are assuming it is downward. We do not like to see negative sign every time, so sometimes we omit it. Okay, so W is keep per feet up to this portion, so keep per feet. As my E and I is inch to the power 4 or inch, I should convert it to keep per inch. Then I converted my span into inch. 8, make sure you can use it. It is not, this is L, not L by 2. So total length, although I have no load here, this equation is derived in a way that the load is in the 50% of the beam. So this way we calculated 0.0095 inch downward because there's a negative sign here. Now if we use positive sign here and get a positive number, that means as it is negative. If we use positive sign here but if you get a negative number, that means opposite. So make sure that whatever you are using, you know it. Then we will find the deflection for this. The equation is this, we just saw it. A means here to here 7 feet, L means total 8 feet, then everything else is known. So this time P is a concentrated load, 3 keep, and E is KSI, so keep messing. Okay, and inch, KSI inch to the power 4, so my L should be in inch, and 3L, say 3, L is 8 feet times 12, and then A is here 7 feet is this. So we calculated both and both we got positive. That means whatever we assumed is correct. So both are downward because we assume downward is positive. There is no sign here. Okay, so if we sum up, we will get the total load. Now this method is very basic method. It has lot of assumption, simplification. This may not be true for real beam which is heavily loaded. It's for linear elastic region. We will see another example here. So you can see my examples is becoming difficult step by step. Now this example, there is a simply supported beam and there is a overhanging portion here, so we can call it a overhanging beam. From here to here is 8 feet and I have a load 4 feet, that means 50% is load. There's nothing here, the beam has no self weight, and E is given, I is given. Question is asking what is the deflection at point C, that means what is the deflection here. Now if you go to the table, you will never see this kind of beam. So what to do? If you go back to the table, you will not see any beam like this. You will not see any beam like this because whatever I listed is uniformly simply supported and cantilever. There is no overhanging beam here. There is an overhanging beam here, but again that is not fully identical. So what we will do, we can use alternative way. What is that alternative way? You can see our beam is similar to this. There is overhanging portion here. Now at this point the slope here and the slope on this side should be equal. So slope here should be equal, and for this kind of beam we can find the slope here. What is that? Theta 2. Theta 2 is here, theta 1 is here. 7 WL square by 384 EI. W means uniformly distributed load. L means total span. So we may use this. Let us see how I use this. Yeah, this is the beam. So for this beam, what we can assume? We can assume the deflection shape is similar to this. Now the theta B, just left of B and right of B should be equal. Why? Because we are assuming linear elastic. The beam is linear. So the beam is linear here. So whatever the slope here should be the slope here. So we will find the slope here first. Once we know the slope here first, using a trigonometric rule, we can find the height. So first we found the slope, which is 7WL to the power 4. Whatever I discussed just a few seconds earlier, that is the slope at this point. So we found our slope 3.98 degree. First we determine, all the equation will give me slope in terms of radian. I told you earlier also, whenever there is an angle and that is detached from sine, cosine or tangent, that angle gives result in radian. If there is a cosine here, that means that will be degree. If it is a separate or detached angle, that will give the result in radian. So whatever it will give you, it is in radian. I convert it into degree. So I know the slope here degree. Then I can use the tangent rule. How? Because if I draw a triangle here, my deflection say here B, or something else also. Sometimes I use B, sometimes or I use Y. See, I used Y here, sometimes I use B here. Both are same. I got confused because when I took this formula, I saw two books. One book used B for deflection, one book used Y for deflection. So when I copied or when I took the material, uh, I did not make it consistent. So in next revision I will make it consistent, either B or Y. But B and Y are both are same, is deflection. So I showed here B, but in my equation tangent theta is Y by 2.5. 2.5 is this distance. So it's actually B and Y is the same thing. It's just some typos. As I was doing it very quickly. So yes, if we use tangent rule, I can find the B or Y, whatever it is, and by geometry we can see that this will go up, this will go up. We should not always use the sign negative positive, because if we do not feel it, it may confuse us. Better to feel the beam. If I apply load here, the beam will deflect this way, it will go up, obvious. Now if there is a load here, that is a different story, but there is no load here, it will be complicated. We do not have that kind of equation to solve it. In this class we can solve only very basic beam. So hopefully you understood. In this case, if something doesn't match exactly in the table, how can we solve it? So I showed you three examples. One is very simple, one is second one is superposition. Yeah, this example was superposition. If you have multiple load, how to do it. And then other example, the last one, yes, if it doesn't matches exactly, how to find it using the information given. So hopefully you got some feeling or some understanding about deflection, and keep on practicing. In the next video we will post something else. Thank you.